Hello students, welcome to the lecture on matrices, and after this lecture we will be able to learn following objectives. Explain the sum of matrices. Explain the product and inverse of a matrix. Describe the adjoint of a matrix. Let us start with the introduction to matrices. A matrix is a collection of numbers ordered by rows and columns. It is customary to enclose the elements of a matrix in parentheses, brackets or braces. Example of matrix is shown on screen. This matrix has 2 rows and 3 columns, so it is referred to as 2 by 3 matrix. The elements of a matrix are numbered in the following way as seen on screen. That is, the first subscript in a matrix refers to the row and the second subscript refers to the column. It is important to remember this convention when matrix algebra is performed. A vector is a special type of matrix that has only one row or one column. Here, A is a column vector while B is a row vector. A scalar is a matrix with only one row and one column. It is customary to denote scalars by italicized lowercase letters. Vectors are denoted by bold lowercase letters and matrices with more than one row and one column denoted by bold uppercase letters. A square matrix has as many rows as it has columns. Matrix A is square, but matrix B is not square. A symmetric matrix is a square matrix in which x of ij is equal to x of ji for all I and j. Matrix A is symmetric and matrix B is not symmetric. A diagonal matrix is a symmetric matrix where all the off-diagonal elements are 0. Matrix A is diagonal, which is as shown on screen. An identity matrix is a diagonal matrix with one S and only one S on the diagonal. The identity matrix is almost always denoted to as I. Real and complex matrix, as in the case of vectors, the components of a matrix may be real or complex. If they are real numbers, the matrix is called real and complex otherwise. For the present exposition, all matrices will be real. Square matrices. The case M equal to n is important in practical applications. Such matrices are called square matrices of order n. Matrices for which M not equal to n are called non-square. Square matrices enjoy certain properties not shared by non-square matrices, such as the symmetry and anti-symmetry conditions defined below. Furthermore, many operations such as taking determinants and computing eigenvalues are only defined for square matrices. Consider a square matrix A is equal to matrix A of ij of order n by n. Its n components of A of ij form the main diagonal, which runs from top left to bottom right. The cross diagonal runs from the bottom left to upper right. The main diagonal of the example matrix is 12, 24, 11, and the cross diagonal is 2, 24, 3.
This video is regarding general introduction about matrices. According to definition, we can say that matrix is a tabular representation of data. Now let's take an example of a matrix. For example, we have A equal to 1, 2, 0, 3 here. So this is a tabular representation of data, we can say that. and this A is a name of matrix. This is name of matrix, and here is actual data that we have regarding a matrix. Usually a matrix, the data is enclosed in square brackets, but you can also use curly brackets for that. For example, you could also write A equal to curly brackets 1 2 0 3, but in my entire videos I'll be using the square brackets. Now the basic question which can be asked regarding matrices is, what is an order of a matrix, or they are also called dimensions of a matrix. The second question is, which can be asked regarding matrices, is how to locate a particular element within a matrix. Now coming to the order of a matrix, what is the order of a matrix? For example, we have a matrix A equal to 2 3 5 6. Then order of this matrix is 2 cross 2, because there are 2 rows. This is the number of rows and this is number of columns. Now in this matrix, when you look, there are 2 rows, this row, second row, first, second. So there are 2 rows and there are 2 columns, 1 2. There are 2 columns. That's why the order of this matrix is 2 cross 2. Now taking another example, if you have something like 1 2 3 4 5 6 here, it's another matrix. Then what is the order of this matrix? The order of this matrix is 2 cross 3, because there are 2 rows. This is row 1, row 2, and there are 3 columns, 1 2 3, 1 2 3. So the order of this matrix is 2 cross 3. In a similar way, if you are given any matrix, any random matrix, you can now find the order of that matrix. The order of this matrix would be 3 cross 2, because there are 3 rows in this matrix, 1 2 3, 3 rows, and there are 2 columns, 1 2. So the order of this matrix is 3 cross 2. So it should be clear about how to find order of a particular matrix. Now the second question is, in any given matrix, how we can locate location of a particular element. For example, we have a matrix A and it is equal to 1 2 3 7 8 9. Now what is the location of this particular element, which is equal to 2? Okay, just have a look in which row it is present. It is present in row number 1 and it is present in column number 2. This is column number 2 and this is row number 1. So the position of this element is A1 2. This 1 is row number and this 2 is column number. Now find the location of this element 9. The location of this element 9 is in which row it is present. The row in which the 9 is present is row number 2 and the column is 3. So the position of this element 9 is A23. Now if you are given any location, let's suppose that you are given A22, then you should be able to find which element is present at this location, A22. So second row, second column, it's 8. Second row and 8 in the second column. So at A22 position, the element 8 is present, the number 8 is present.
Let us understand some of the matrix. If A and B are matrices of the same size, their sum A plus B is the matrix formed by adding corresponding entries. If A is equal to A of ij and B is equal to B of ij. Hence, the sum of these two matrices are as shown on the screen. Note that addition is not defined for matrices of different sizes. See an example of matrix sum on the screen. Students, now we will talk about the matrix algebra determination. Matrix multiplication. If A is an M cross N matrix and B is an N cross P matrix, then C is an M cross P matrix. We use C of ij to denote the entry in row I and column j of matrix C. Standard row times column. The standard way of describing a matrix product is to say that C of ij equals the dot product of row I of matrix A and column j of matrix B. Columns. The product of matrix A and column j of matrix B equals column j of matrix C. This tells us that the columns of C are combinations of columns of A, rows. The product of row I of matrix A and matrix B equals row I of matrix C. So the rows of C are combinations of rows of B. Column times row. A column of A is an M cross 1 vector and a row of B is a 1 cross P vector. Their product is a matrix. The columns of this matrix are multiples of the columns of A and the rows are multiples of the row of B. If we think of the entries in these rows as the coordinates 2, 12 or 3, 18 or 4, 24, all these points lie on the same line. Similarly, for the two column vectors, we will see that this is equivalent to saying that the row space of this matrix is a single line, as is the column space. The product of A and B is column times row matrices. Blocks. If we subdivide A and B into blocks that match properly, we can write the product AB is equal to C in terms of products of the blocks. Inverses of matrices. If A is a square matrix, the most important question you can ask about it is whether it has an inverse of A. If it does, then see on screen. Here we say that A is invertible or non-singular. If A is singular, that is, A does not have an inverse, its determinant is 0, and we can find some non-zero vector x for which Ax is equal to 0. Example of A inverse is as shown on the screen. Gauss-Jordan elimination. We can use the method of elimination to solve two or more linear equations at the same time. Just augment the matrix with the whole identity matrix I. We can write the results of the elimination method as the product of a number of elimination matrices E, Ij with the matrix A. Letting E be the product of all the E, Ij, we write the result of this Gauss-Jordan elimination using block matrices. Matrix transpose. The transpose of a matrix is denoted by a prime or a superscript small t or capital T. The first row of a matrix becomes the first column of the transpose matrix. The second row of the matrix becomes the second column of the transpose, etc. The transpose of a row vector will be a column vector, and the transpose of a column vector will be a row vector. The transpose of a symmetric matrix is simply the original matrix. Now we will discuss determinant of a matrix. The determinant of a matrix is a scalar and is denoted as determinant of A. The determinant has very important mathematical properties, but it is very difficult to provide a substantive definition. For covariance, and correlation matrices. The determinant is a number that is sometimes used to express the generalized variance of the matrix. That is, covariance matrices with small determinants denote variables that are redundant or highly correlated. Matrices with large determinants denote variables that are independent of one another. The determinant has several very important properties for some multivariate stats, that is, change in R square in multiple regressions can be expressed as a ratio of determinants. Here we will use the inverse matrix to solve equations. One of the most important applications of matrices is to the solution of linear simultaneous equations. Writing simultaneous equations in matrix form. Consider the simultaneous equations as shown on the screen. These can be written in matrix form as shown on screen. This is the matrix form of simultaneous equations. Here, the unknown is the matrix X, since A and B are already known. A is called the matrix of coefficients. Solving the simultaneous equations. See on screen. We can multiply both sides by the inverse of A provided this exists as shown on the screen. Here, multiplying any matrix by an identity matrix of the appropriate size leaves the matrix unaltered. So the result is shown on the screen. This result gives us a method for solving simultaneous equations. All we need to do is write them in matrix form, calculate the inverse of the matrix of coefficients, and finally perform a matrix multiplication. Let's now talk about adjoint of matrix. In linear algebra, the adjoint matrix of a square matrix is something similar to the inverse of a square matrix. When A is invertible, the difference between adjoint of A and A inverse is just a scalar. However, the adjoint matrix can be defined for any square matrix, not necessarily invertible. Now let us look at the list of properties of adjoint matrices.
Adjoint of a matrix. The concept of adjoint is defined only for square matrices. If A is a square matrix, then the adjoint of A is defined as the transpose of the matrix obtained by replacing the elements of A by their corresponding cofactors in det A. The adjoint of A square matrix is denoted by adjoint A. To find the adjoint of a square matrix, replace all its elements by their respective cofactors and then find its transpose. For example, if matrix A has elements A11, A12, A13, A21, A22, A23, and A31, A32, A33, then replace each of the elements by its cofactors as shown. Now we need to find the transpose of matrix of cofactors. This is done by writing the rows of the matrix of cofactors as columns to form the adjoint of the given matrix as shown. So we get adjoint A. Click on the button Numerical. Now, try out this simple problem on a 2 cross 2 matrix and find its adjoint. Find the adjoint of the matrix -1, 5, 3, -2. To find adjoint A, we need to first find the cofactors of -1, 5, 3, -2. That is, we need to find A11, A12, A21 and A22. Key in the value for A11. Use the OK button to check your typed answer. Else, use the Solve button to get the value. Go ahead and solve the problem.
Let us now discuss how to find the adjoint matrix. The adjoint of a matrix A is found in stages. Find the transpose of A, which is denoted by A superscript T. The transpose is found by interchanging the rows and columns of A. So, for example, the first column of A is the first row of the transpose matrix. The second column of A is the second row of the transposed matrix, and so on. The minor of any element is found by covering up the elements in its row and column and finding the determinant of the remaining matrix. By replacing each element of A superscript T by its minor, the cofactor of any element is found by taking its minor and imposing a place sign according to the following rule as shown on the screen. This means, for example, that to find the cofactor of an element in the first row, second column, the sign of the minor is changed. On the other hand, to find the cofactor of an element in the second row, second column, the sign of the minor is unaltered. This is equivalent to multiplying the minor by +1 or -1 depending upon its position. In this way, we can form a matrix of cofactors of A, T. This matrix is called the adjoint of A, denoted ADJA. The matrix of cofactors of the transpose of A is called the adjoint matrix ADJA. Now, in the end, let us summarize what we have learned in this lecture. A matrix is a collection of numbers ordered by rows and columns. It is customary to enclose the elements of a matrix in parentheses, brackets, or braces. A vector is a special type of matrix that has only one row or one column. A scalar is a matrix with only one row and one column. A diagonal matrix is a symmetric matrix where all the off-diagonal elements are 0. The components of a matrix may be real or complex. If they are real numbers, the matrix is called real and complex otherwise. Square matrices enjoy certain properties not shared by non-square matrices, such as the symmetry and anti-symmetry conditions. The minor of any element is found by covering up the elements in its row and column and finding the determinant of the remaining matrix.